Hello and welcome to section 3.4, concavity and the second derivative test. Here are the examples for this section. Remember, if you have any questions for these, please come to class with them and we will talk about them. So in the first one here, they're asking us to determine the concavity, and that's basically what the second derivative test does for us, is gives us concavity. So in order to do so, we've got to go through and find the points where the second derivative is equal to 0, because that will help. Those are what we call points of inflection, changes in concavity. So we're going to go through and find those. So f prime, so we got to just start by doing the derivative. So we'll start with f prime, and this is basically kind of like a quotient rule. Actually, I'm going to treat it like a chain rule, and it's going to be 6 times x squared plus 3 to start with. We'll just do it as a chain rule, and so that's what our function is rewritten. And if I go ahead and do the derivative of this chain rule, I get negative 6 times x squared plus 3 to the negative 2, and then the derivative of the inside is just 2x. So the first derivative gives me negative 12x divided by x squared plus 3 squared. And so now, in order to get the second derivative, I've got to go through and actually do a quotient rule on this, because I can't simplify it. So I'm going to move over here and do the second derivative. And so to do the second derivative of x, derivative of the top gives me negative 12 times the bottom. And then subtracting away, leaving the top alone. Must be an x in there. So negative 12x, derivative of the top, leaving the top alone. And in order to take the derivative of the bottom, I have to, in order to take the derivative of the bottom, I'm going to have to use a chain rule. And so that's going to be the 2 times the original function, reduced power by 1, and then the derivative of the inside, which is 2x. And so then all of this guy is going to be over the bottom squared, which makes it, instead of squared, to the 4th power. And so now I actually have to do some simplification on this to make my life a little bit better, and it just depends on how we want to go about this. Let's see what I can do here. I'm just going to leave that first part alone, just see if that will help me. I don't know. We'll see. And then this guy is going to be 4x times. So I'm going to end up with, let's see, I've got 4x and positive 12x. So that's 48x squared. And all of that is times this thing. And so if I was to factor out an x squared plus 3, then you could see that I would be left with something like if I factor out the x squared plus 3 top and bottom, then I will lose 1, and so I'm left with negative 12 times x squared plus 3 plus 48x squared, and all of this then is divided by x squared plus 3, not to the 4th anymore, it's now 3rd, because we removed one of these guys from the top and the bottom. So then the last thing, to just make this a little bit easier, if I distribute the negative 12x squared, I get negative 12x squared minus 36x minus 36, and then plus 48x squared. And so then you can see that this thing's going to get a little bit better. And so then I will have a negative 30, I'll have a 36 in common, and so I can get 36 times x squared minus 1 all over x squared plus 3 cubed. Did I need to do all this simplification? Most likely, because I now, since to find the places where the graph is changing concavity, I need to set this second derivative equal to 0, and when I set that equal to 0, I can find that. Well, when I set it equal to 0, if I set the bottom equal to 0, it become imaginary numbers, which we don't want, so we're not going to deal with the bottom down there. So we really only set the top equal to 0, and when we set the top equal to 0, if I divide by 36, I'm really left with x squared minus 1 equals 0, so x will be plus or minus 1. So those are the points that I'm looking for. So now I just need to set up, just like kind of like we did with the first derivative test, negative infinity to negative 1, and just put a little line there, and then from negative 1 to 1, and then 1 to positive infinity. And so I'm going to check the concavity around this, and basically I just have to pick a test value and plug it into the second derivative. So into my second derivative, I'm going to plug in, say, negative 2, and again, I don't care about the actual number, I just care about the signs that I'm going to get. And so when I plug in negative 2 into the top up here, I get 4 minus 1, which is positive, which then means the top is positive and the bottom is positive. So I end up with a positive number. So right there, we know we are concave up, because a positive would be concave up, a negative will be concave down. So then I'm going to put f double prime of 0, plug 0 into this because that's between negative 1 and 1, and by putting 0 in here I get a negative on top and a positive on the bottom, which gives me a negative, so we are concave down. And then between 1 and infinity, I'm going to try a number like 2, and plugging that in I get a positive on top, positive on the bottom, so we get a positive, so we are concave up. And that's really all we're trying to do. Some people like to draw the pictures to represent them, but that's really all we were trying to do with this one. So then the next one, we're trying to find the open interval of the graph where we're concave up and concave down. Same type of deal as what we were just dealing with. So again, we have to do the second derivative. And so I have to do a quotient rule on this one. And so derivative of the top will give me 2x times the bottom. And then subtract away, leave the top alone. And the derivative of the bottom, all over the bottom squared. And so then continuing on a little simplification, I get 2x cubed minus 8x minus, looks like, minus 2x cubed and positive 2x. Wait, that's not right. How about a negative 2x? And we get a negative 2x. And, hold on, negative. I lost it. Should be a positive 2x. So I messed up a sign in here, and so like I said, it should be a negative 2x. That's what I was getting originally, and so I messed up. Since I messed up that sign, I should have a negative 2x down there. And so then all of this guy is still over x squared minus 4 squared. So simplification of the top gives me a nice little negative 10x all over x squared minus 4 squared. And so then I get to go ahead and do the second derivative of this. And so doing the second derivative of this will be derivative of the top times the bottom. And then subtract away, leave the top alone. And again, I'm going to have to move over a little bit, see how far I can. And then the derivative of the bottom is going to take a chain rule, which gives me 2 times x squared minus 4 times 2x. And I just kind of have to write it up there, because I ran out of room. And then on the bottom is the bottom squared. Again, so now it's to the 4th power. And so simplifying this the best I can, you'll notice that I have an x squared minus 4 top and bottom, so I can reduce the number of those that I have. So I'm going to factor one of those guys out, so I'm left with negative 10 times x squared minus 4. Instead of the 2nd power, it's now to the 1st. And combining 2x times 2 times negative 10, I end up with 40x squared. And then that's going to, and that one's gone. And so then this is now, instead of over x squared, x to the fourth, it's x cubed, because it's cubed because I lost one of the powers all the way through when I simplified it. So this is just making my simplification a little bit easier. Distribute my negative 10. I get negative 10x squared minus plus 40x squared all over this thing. And with a little more simplification, it looks like I can factor out a 10 and get 3x squared plus 4 all over this thing. And so now I'm going to set this thing equal to 0, and setting this equal to 0 will give me my points that I'm looking for. And basically, you'll notice that if I set the top equal to 0, I'm going to end up with imaginary numbers. And in this case, I'm going to set the bottom equal to 0, which will give me x equals plus or minus 2. Now, in this case, remember this is going to give me places where when the bottom is equal to 0, this is where the graph doesn't exist. And you probably should have graphed the original graph just to kind of see what was going on there. And when you do that, that's kind of what's happening. You'll see that you have some asymptotes there. But anyway, so when we go ahead and use these values, we're still going to do the number line that we did before. We're still going to check concavity around these. So we're going to go negative infinity, even though they're asymptotes, to negative 2. And then from negative 2 to 2, and then from 2 to positive infinity, and basically plugging in these numbers, a number like them, into the second derivative. So if I do like negative 3, again, I'm just looking for signs, and the top, when I put in negative 3, all is positive, and the bottom, plugging in negative 3, when it's squared, it turns into a positive, which gives me the bottom is positive. So I have a positive number, so we are now concave up. And so it looks something like that. And then between negative 2 and 2, 0 is a good number to plug in there. And so putting 0 in, I'm still positive on top. Putting 0 in, I'm going to end up negative on the bottom. So this is negative. So now we are concave down. And when you look at the graph of this, you can actually see what we're talking about. And you got to remember that some of this stuff is just trying to figure out what the graphs look like without actually graphing them. And then if I put in something like f double prime of 3, plugging in 3 into this guy, positive on top, positive on the bottom, so we are concave up. And that's really all we're trying to do, is try to figure out what's going on. Even though this graph has some asymptotes, it's still concave, the concavity still matches that. In our next example, this time they're asking for the points of deflection and discuss the concavity, so we're going to talk about that, what that actually means. So the points of inflection are what we've been finding when we've been doing the second derivative. So the first thing I'm going to do is find the first derivative of this guy, and that would be something like 4x cubed minus 12x squared. And then if I go ahead and do the second derivative on this, I end up with 12x squared minus 24x. And if I factor out things I have in common to make my life a little bit better, I can factor out a 12x, which then will give me x minus 2. And so to find my points of inflection, basically what I'm going to do is set this equal to 0 like we have been. And by setting it equal to 0, I find out that x is either 0 or x is equal to 2. And so these are my points of inflection. This is where the concavity could change. It doesn't mean it has to. It just means these are the points where it could change. So just like before, I'm going to do kind of a second derivative test on this and say from negative infinity to 0, and from 0 to 2, and from 2 to infinity, I'm going to test my intervals just to kind of see what's happening in those. So I'm going to do a second derivative test. So f double prime of negative 1. Putting negative 1 into either one of these guys will help us out. So if I put negative 1 into the first, I get a negative. Negative 1 into the second, I get a negative. So a negative times a negative is positive. So we are concave up, is what it's telling me for that when I do negative 1 in this interval between 0. So now if I'm still concave up between 0 and negative 2, our point of inflection is a point of inflection, but it doesn't change the concavity, which means that we don't have any kind of maximum or minimum, which we'll talk about in the next example. because we'll use this to help us find maximums and minimums. So then if I do a second derivative of, say, like 1, and putting 1 into this function, I get a positive for the first term, a negative for the second term, and it's negative. And you'll notice in my examples it's always been positive, negative, and stuff like that, or whatever. But it doesn't always work like that, so be very careful when you do these. And then the next one, if I put in something like f of 3, I get a positive and a positive, so we are concave up. And so the points of inflection are basically telling us that the concavity that we're dealing with, and so that's really all we're trying to do. Is when they say discuss the concavity, we want to know that in these intervals between negative infinity and 0, we're concave up, and also between 2 and infinity, we're in that same boat. And then between 0 and 2, in that interval, we're concave down. And so some kind of summary of that would be necessary to discuss the concavity. So then in our final example, we are trying to find the relative extrema, and this is one of the powerful things that the second derivative test can do, because think about it, if I am concave up in there, then I'm going to have a minimum. If I'm concave down, then there's going to be a maximum. So that's kind of what we're looking for, and so we will go ahead and do that in here. And so the first thing we have to do is find our first derivative. So we find our first derivative, which gives me negative 15x to the fourth plus 15x squared. If I factor out my like terms, I get a negative. I'm going to go with negative 15x squared, and then that's going to leave me with x squared minus 1. Now the reason I did this is I'm going to find, remember, maximum and minimums are at our critical numbers. Our critical numbers come from setting the first derivative equal to 0. So that means my critical numbers are 0 for this first term, and then plus or minus 1. So those are my critical numbers. Those are critical numbers. Now we're going to go ahead and go to the second derivative, and when we do the second derivative, okay, so we go ahead and do the second derivative of this, and that gives me something like, let's see, negative 60x cubed plus 30x. And so there's my second derivative, and with a little simplification, I might make it a little easier on myself and do something like 2x, or take out a 30x, negative 30x, and say 2x squared plus or minus 1. That might make my life a little bit easier. I could even leave the x in there. Let's just leave the x in there. Let's go back and leave the x in there. If I just factor out a negative 30, then I would have x cubed minus x. All right, so I get something like that, and that just makes my life a little bit better. But if I plug in these critical numbers into the second derivative, and they get me a positive number or a negative number, then I'll have a relative max or a relative min, because remember, we said if it's positive, if our second derivative, whatever it is positive, we're concave up, which means that value, which could be which is our critical number, will give us a minimum. If our second derivative comes out to be negative, then we're concave down, and we're plugging in the critical numbers, which are basically where the maximum and minimums could appear, and it'll tell us that that's what we're dealing with. So if I'm going to plug in these numbers, my critical numbers, into the second derivative and say, okay, well, f double prime of 0, plugging in 0 gives me 0. So at this case, when we're equal to 0, this is where the test fails. It's no maximum or no minimum. It actually gives us a little more information. We'll talk about that in class. If I plug in f double prime of negative 1 into this function, again, I'm just looking for signs. Negative 1 will give me a negative here, a positive, and so this should be, I should get greater than, this is positive, this is, negative 1. I lost a 2 there. That's what happened. So plugging in negative 1, this gives me negative 2. This gives me a positive 1, which gives me positive 1 inside. So then I end up with a positive number. And so this gives me that I'm concave up, which means that I have a relative minimum. And then if I do the second derivative and plug in positive 1, plugging in positive 1 will give me a negative number, which is less than 0, which gives me a relative maximum. So we'll talk more about the second derivative test in class, so please come prepared with your questions, and we will talk about this.